The talk we're going to present today is about how to organize the game between language models. Like you can, like two language models to fight with each other, and in the end, like we're gonna see like what kind of things we can get from the game after we play several rounds of that, also fights. So you know, like well, let's say I first bring that the context. Like this work is a joint work with University of Notre Dame and KAUST, which in Saudi Arabia. I usually have a collaborator there. They work on language models. They work on also training methods for deep networks. So now we step into the world of large language model, how it goes with the classical way of also training. So let me just give you guys like a little context information. So what is adult training and what is adult attack? So when we talk about adult attack, and this is a famous example, like you have an image and you put some noise here, and the image is misclassified. So I remember, like if you search in Google, the first image you can find, if you put adult attack as a keyword, and you're gonna have image like there's a panda, and you put a noise there, and it misclassifies as a monkey. This is the stuff like that, which means the deep neural network has a instability inside. Like you slightly change the input, then the output will be drastically changed. So that's the core issue. So how to make the deep neural networks robust enough? So previously there are many ways, tons of papers talk about how to robustify the neural networks. Basically, you can divide into two parts, like, or you say, I want to smooth the neural networks. So I want to say, I put some regularization, put on the neural networks, make sure the classification boundary is smooth enough. And in the end, okay, you can have less mistake over the initial samples, but meanwhile, you're going to lose some utilities, which is one way to go, to regularize the complexity of your model. So the other way is around the adversarial training. So I know you're going to make mistake over some adversarial samples. I prepare these samples for you. I give the correct labels for those adversarial samples. I give you all the training samples for retraining your model. And in the end, you should correctly classify those adversarial samples as output. So this is called adversarial training. And also, there are some theoretical studies trying to set up the adversarial risk bound of deep networks, arbitrary deep networks. And this is basically follow the original theoretical study in the statistical learning proposed in the 1980s. The famous Professor Wapnick, he proposed the whole framework. So now, like all the machine learning models that we say follow this framework until now. But then this is what we have for usually the adversarial training technique that you play with. So basically, this is a min-max optimization. You can intuitively, it's like how I can generate some of the sample that you can have the highest likelihood to make misclassification. And this adversarial sample will be called like a worst case example. That means like you are the most likely to make a mistake over these samples. And I want to minimize your classification risk over those worst case samples. And if you can minimize the classification risk over these samples, I can make sure like over the other samples, like in other better situations, you won't have misclassification likelihood. So that's the basic logic. And this is the mathematical formulas we play in adversarial training. And I can guarantee like this is the only formula I'm going to show today. So there are two optimization problems we're going to solve. So inside is the generation of adversarial samples. So X is the input, and delta is the noise, the adversarial noise you want to inject into the input. And what you want to do is like, let me just add some noise here, and I want to maximize the classification risk over the output of this classifier. That means like I want to find a noise that can mostly improve the misclassification likelihood over the classifier. Then this is called the worst case adversarial sample. So when you solve this problem, you get delta, and you have the X data and the true labels. And this forms the set of adversarial training samples. And the outer layer of the problem is trying to minimize the classification risk over the adversarial samples that can help your classifier to be resilient over the adversarial noise. Right. So this is the formulation. And in practice, we just play the optimization in 2 rounds. Like first you generate something and you minimize. You generate something, you minimize in the several rounds like that. So, change. So basically, when you do the training in practice, what you do is like, let's first freeze the classifier. Let's keep the classifier as it is. We don't change any parameters. Let's generate the worst case adversarial samples using the optimization method like FTSM or PGD, project a gradient descent way to generate the adversarial samples. And you have them. Once you have them, you keep the adversarial samples, and then you use the gradient descent to update your classifier based on the knowledge about what is noise adversarial attack and what's the true labels of the adversarially perturbed input. So you play this round for several iterations. In the end, the training hopefully will come to be converged. And once you convert, you get classifier robust enough to the adversarial attack. So this is the current practice. Well, I would say this is the current, the best strategy that we can apply for deep neural networks to defend the adversarial attack, but it's not applicable for the large language model. So supposing like we're talking about GPT 3.5, so 175 billion parameters, and GPT-4 is even bigger. And let's say some of you already play with the Llama 7B. And this is already big one. So if you want to retrain, and this is a big task. Let's say like personally, I tried retraining myself on the G5K. So basically, if you want to retrain a Llama 7B, which is a basic model, you're gonna need 4 GPU card, like 400 GPU card for fine tuning. But yes, you can have technique, but basically that's the requirement. And I don't think any of us can afford such a computation cost. That's one thing. The other things like how you organize this like attacks against the language model is still an open question. So let's say we have some prompts that can help us to attack, but in the end, there's no framework for us to generalize a pipeline to produce more and more prompts for attack. So that's the current bottleneck. But let's remember like a GPT-based model still, it's a deep neural network. It's nothing more. Okay, so it's just more complex, but of course it's still a transformer model. Right, so it should have the same vulnerabilities as deep neural network intuitively. Yes, there's no proof, but when the model becomes more complex, and then you have more adversarial vulnerabilities. This is decided by the nature of the statistical learning. You're going to have like a more complex model. You have less generalization capabilities over the non-ID data points. So that's why like we have the problem here. There's a adversarial vulnerability for language model. You can demonstrate, but then how to generate attacks efficiently and how to define the defense strategies against such attack. So this is the problem we want to attack in this study. All right, so then before we dive into technical details, let's say there are some potential demonstration or potential use case for the attacks against language model. So one of the famous attacks is called jailbreaking. That means like, like a language model is always fine-tuned and fine-aligned. They shouldn't answer any question contain malicious contents. For example, if I ask GPT-4 to generate a method, help me to produce a bomb, potentially probably you won't succeed. Okay, he can refute the answer. But there are some ways, if you carefully tune your prompts, you can let language model the answer if you take these prompts as input. All right, so this is called jailbreaking. And of course, there are other attacks like a prompt injection, like you have a paragraph, and inside the paragraph as input, you just add one instruction to let language model to visit some spearfishing page, just one sentence in the middle of the paragraph. And then the language model will take the action over each line of the paragraph one by one. And when it jumps to this line of spearfishing page visiting instruction, language model will execute that. So this is called a prompt injection. That means like language model doesn't really understand what's going on with instruction. This instruction, I'm gonna execute that. That's it. So this is called the prompt injection. And of course, like there are also some guys trying to play tricks with language with GPT for trying to understand which kind of prompts that the OpenAI was using. So this is called the prompt leaking attack. Again, if you have these attacks applying the safety critical areas, we're going to have a malicious outcome. For example, here. Okay, so this is a simple check, right? So normally, if I say I want to body someone, you shouldn't answer, right? So this is the error sneak issue. But then if you use some prompts as the input, and then it can answer. It can answer how you can do that step by step, and this is not allowed. So, but again, this is not for system security. It's for social security and information alignment. And then you can say, here I want to produce some medicines that shouldn't be allowed for me to produce. And if you take some prompts like, I imagine you are taking some roles, you're taking roles of my granny, and then let's tell a story how to make use of the chemicals that I have to produce some medicals. And yes, you can answer this step by step because he thinks this is just a story. It's not a fact. Okay, so this is another way that people can leak really dangerous information out. But then the prompts can be not semantically meaningful. They can be just like a random codes there. Again, the random codes can be tuned, and you can try them for 1,000 times and choose one of them can work out. So they just put some random strings there, and output can be malicious. So this is another way that can change the activity of language model. For us, I think the interesting stuff is like, there are some dark GPTs, like a GPT fine-tuned to the malicious data to generate the strategy for cyber attacks. And one of the products on the darknet is called the Worm GPT. If you search in Google, I think you can find some example of Worm GPT. So you can provide the protocols, network protocols, configurations to the Worm GPT. Ask the Worm GPT, what can I do to sneak into such a system? How can I do to find out the vulnerabilities? They can suggest you some steps to go. Then this is not supposed to be the response of the legal GPT. In darknet, there are tons of stuff like that people fine-tune the open source, the closed source, the GPT model, GPT-like model, that they can be adapted to the specific use generating spear phishing emails, right? To guide you how to produce a simple malware. Okay, so how to guide you how to sneak into the system by exploiting the known vulnerabilities given the network protocols or configurations. These are the things even more than simply impacting the information alignment error sneak issue. And this is really dangerous that people can use this to speed up their cyber attacks. So these are the things we want to mitigate when we use the GPT-based model for knowledge retrieval. Okay. All right, so this is another stuff like given some background information, they're going to generate the spear phishing emails, and then you can write up, send to the customers. All right, so let's back to the technical part. So when you want to tag language model, there are many ways to go. The simple way, yes, you write yourself. You try, you take the role of a malicious attacker. What you want language models to do. So you write your prompts yourself, and you're gonna try. I think my colleague at the US, they try they recruit a group of students, write about 2.5K prompts and try each prompts one by one until I found some of them can work out. And that language model, induce language model to output something really bad. But then this is the basic way. So another way to go is can we all observe the gradients or the embedding change when we change tokens as input because let's say language model is still a deep learning model, right? So what caused deep learning model unstable is like if you change the input slightly, the inside embeddings of the feature space will be drastically changed for the input, and that's why we trigger the misclassification. So this is the reason. And same thing for language model. If we can look into the embeddings and say, if I replace this token, replace this word, replace these characters, if I misspell some words, if I replace the sentence with the others, what will be the change in the embedding space? If the embedding space will be drastically changed from one space to another space, of course, this one will be my target tokens, target characters to change, to trigger this misclassification or the mis output. So this is the way, another way to go. Basically, you can divide the tag into two branches. One is like a white box. You have fully access to the whole model. You can observe the embeddings inside. You can manipulate the model even by retraining the model. And then you can observe the models inside the feature space change by query the change of the tokens. And then you can say, okay, which tokens will be the most sensitive for me to change. So this is a white box way to do. And then it's like a black box way to do. And like I said, the simplest way, you write yourself, you try until you find someone that works out. Still, there are already some database, unfortunately, they're releasing, releasing everywhere on the internet. I can search jailbreaking prompts that works out there for GPT-4, and you can find a list of them. So nobody can really put a control of that because it's hard to recognize they're malicious or not. And then you can generate the new prompts based on the already published prompts. Like for example, I can combine two prompts together and to find a better way to attack. That's doable. And also you can simply say, I can just rephrase some 10 sentences inside. This can be another way to generate the new prompts. So this unfortunately is to be let's say a risky source on the internet that people can make use of to attack. And this is a black box. You don't really care which model will be your victim. You only care about how I can figure out, write out the new ways of rephrasing the prompts. All right. So these are the two branches attack that we're facing to. So I think the researchers they're trying to do something to mitigate such an attack, trying to enforce alignment between the language model's output and arsenic rules, politically correctness, or fairness, like should be aligned with human value. And this is what people do in the past 5 years with the industrial practice. For example, like the DPO, like direct policy optimization and supervised fine-tuning. And this method are very popular nowadays to train the language model. So last month I talked to guys from from ISTA. So they are trying to use the DPO stuff. They're collecting the samples. It's just like supervised learning. Collect samples, and the input samples can be the jailbreaking, can be the prompt injection samples. And output should be their expected output, which is aligned with human values. And they collect some samples like that, pull into the training pools, and try to retrain the language models. So this is the way people play with nowadays. Another way to go, of course, the deep neural network tells us you can also try to control the complexity of the model. But this one is not quite applicable. For a large language model, supposing you have hundreds or even thousands of layers, so which layer you should put this complexity control, you should enforce this regularization is unknown. There's no theoretical guarantees. And that's why it's not the mainstream method so far. Then the bottleneck is this DPO and SFT-based fine-tuning method is not usable for most of the cases. Supposing you want to create a startup, and then you can have maybe a machine with 4, 5 GPU cards, and then you don't have access to the really big web-scale database. How can you do this fine-tuning? And if you can do the fine-tuning, how can you pack up the GPT-based model to produce your own products for the customers? So this will be a bottleneck for most of the, let's say, downstream developers for the GPT-based model. So that's why, like nowadays, retraining-based method, they only there will be the best choice, but they will be the choice only for the big industrial practitioners. So what shall we do for us? How to improve the language models' robustness? The other way to go is like, let's try some in-context learning technique. All right, so what is in-context learning? So for in-context learning, you can imagine you're talking with someone who knows everything. Language model knows everything because it trained with everything. All right. And then you should specify your question. Otherwise, like you can suppose, like if you ask someone, you don't specify a question, and this guy will not answer you precisely what you need. So the in-context learning is the way, like how you design your way of asking. So in asking, the way of asking in language model is to design your prompts. So for example, recently I have been working on the knowledge graph traction using language model. So David, you know us about, so we're using language model to do code declaration, to cheat the code checkers using language model. All right, but then you have to specify your problem. For example, if I want to cheat the code summary, I want to say I add something to code, I change the identifiers, for example, but I want to misclassify the code functionalities. All right. And then this one, you have to specify which kind of options you can adopt to change the code. For example, should I only change the identifier's name? Should I adopt some obfuscation, like I just add some data control flows in the code? Should I add some nested functions implementations in the code? Should I use dynamic function loading? So there will be many techniques, but you cannot just blindly say, change the code, decorate the code. This is too rough. And language model will not give you the accurate answer. So what you can do is like specify the concrete actions or strategies the language model will be instructed to take. And then clearly define your goal. For example, in our goal is like, okay, I want to decorate the code with the options I offer to you. So in the end, the code summary output from this language model will be different from the clean code. This is our goal. And with this prompt, we can do whatever we want to change the code, and we can get what we want. But if you only use one simple sentence, say, change the code and cheat language model, they will answer nothing. They will give you rubbish. So this is how prompts works out. All right. For knowledge graph extraction, the same. Because I want to generate, for example, I want to extract the family of malwares and CVE numbers, and when the attack was observed, what is the AP campaign, right? So what is the attack surface? What's the attack chain? So these are the stuff you need to provide some example to language model. Otherwise, he wouldn't understand what is attack chain, what is the CVE number, okay, what is the malware family name. You have to provide some example so that they understand what kind of things I want to identify and extract from the reports. All right. So these are the prompts. If you ever know Bayesian inference, so you can say the in-context learning, basically you set up a prior probability or prior distribution you want to sample the variables from. And then he will just sample the variables within the prior probabilities, prior distributions, and your decision will be made based on the Bayesian rules, like the post-maximum, the post-area probabilities. So this was exactly the role of in-context learning here in language models generated text. There was a work published 2 years ago by Stanford. They're trying to set up the bridge between Bayesian inference and in-context learning. So I can provide you the links, and if you feel interested, you can read. Really interesting. All right. So these are the in-context learning. So then if you say, I want to define some defense based on in-context learning, means you can extract some rules that language model can follow. For example, if I see some keywords, the input queries from the user, I should refuse the answer. For example, I see bomb, I should refuse the answer. All right, but this could be over defensive. Let's say it can be accumulating. If I see several keywords together and these keywords are very dangerous in my list, I should pay quite high attention to this input. I should choose to refuse to answer. Otherwise, like if there's no keywords that I feel sensitive, so okay, I can answer this question. So something like that. The rules will be generated, and these rules will put as the system prompts of language model. Talking about system prompts, it's like when you load the language model, if you program that, when you load language model, you are allowed to set up a set of sentences that every time language model receive any query from outside, this sentence will always add before the user query. And this is called like a system instructions as well. So this is the opportunity for us to set some barriers, to check the input, and to check if I can answer the question from the user or not. So this is the basic idea. But then how to extract such rules, or how to extract such signatures, and this is the question mark for us. Talk about like signature. So if you guys play with malware, and you know like there's YALA rules. So for YALA rules, this is signature. The strings, something you can observe from the binaries, right? And also VerseTotal set up its detection, mostly detection on YALA rules before you really reruns the samples in sandbox. Okay, but then how you generate such rules for language model? For malware, we know we have thousands of experts every day sitting down just looking at binaries and extract the strings. For language model, we don't have. We only have several APIs on our own. How can we do that? So the ways like trying to organize the competition between two famous language models. For example, I have GPT-4, I have GPT-3.5. One's attacker trying to generating as many as possible attack prompts by changing the phrases, changing the characters, replace orders, like changing the orders of the sentences, like rephrase the whole paragraph. This will give us a diversity inside attack prompts. Some may succeed, some may fail. We don't know. We just try. We just enlarge the diversity of the attacking prompts. And we have already, and I have also like another role for tender, like for defender, like GPT-3.5. That this one is just for receiving the attacking prompts from the attackers. And I receive the attack prompts. I observe my feedback. Some questions I just induce to answer. Some questions I refuse to answer. If I induce to answer, then that means like the attack succeed. For the failure case, that means my model is safe. Okay, so from this case, I can try to learn. Okay, so which kind of inputs patterns or string patterns that I feel sensitive, I should avoid answer such question if I see these strings. These are the goals for this game. Like one is trying to enlarge attack powers, and the other one is like if you increase your attack power, so this way I can check what's my vulnerabilities that can mitigate the second round of game. So once you play several rounds game, we hope once the game ended, either we have really powerful attacker or we have really powerful defender, one way or the other round. So hopefully you can end up with second outcome. That's why like we dive into this game. So this is also called like from economic research. This is called a Stackelberger game. Stackelberger game is like both attacker and defender. There are competitive roles and take actions at the same time. Right. So at the same time and before second round of action, each one will take a reflection based on his response to the action of the other one. And based on the reflection, he can update his strategies for the second round. And in the second round, they take the actions again at the same time and redo this reflection. So this Stackelberger game, the concrete case Stackelberger game, maybe you can find in stock market, the financial companies. One is trying to raise up the price, one the other to lower down the price. So this is the typical case of Stackelberger game. Concretely in the machine learning, the typical case for Stackelberger game is the adversarial trend. One, the GAN model, the generative adversarial network. One is trying to maximize the loss, the other one trying to minimize the loss at the same time. So the goal is competitive. Two guys will take the action at the same time, and they will be update their model after they receive the response, their own response, and they observe the actions of the other guys. Okay, so I will talk so much about that, but then how we compose this such a adversarial game between language and model. So I think the most important module inside is like a language model should be able to reasoning, to do the reasoning task. Like say, I receive some attack, and for some attack I mitigate, for some attack I fail to mitigate. And then based on the input, the attack input, what is the question that people ask, what is the prompts that people trying to trigger me to answer. Based on the inputs, what kind of rules I can generate. So in these inputs, is there any patterns that I should follow? So let's say there is a branch of jailbreaking attack named the role play attack. That means like the firstly, every prompt will start with the sentence say, you are playing some roles. Like you're playing some roles of Mike Granny. You're playing some roles of crazy scientist. You're playing the role of Albert Einstein, for example. And then the language model can take this role and answer something they shouldn't answer. All right, this is role play. And then if we put this example for reflection, the things we want language model to summarize, like next time, if someone want me to play the role play game, I have to refuse to answer. That's the safe strategy. And then maybe you can do some more selective things. But then that really depends the summary of language model based on what he receives. All right, so this is called self-reflection. This is already published 2022, 3 years ago. There's a paper about how to use language model to do the summary of his own behavior, and this is called reflection. Okay, so it's bad quality, but then the things like I can give you some interpretations. Like the reflection is like the process. First, I give you the example. I give you the question. I give you a task. For example, can you all right, what's the example? Can you tell me about let's say, how to say that? Can you tell me about the characters of some famous figure? I wouldn't say any name. It's not political right. So can you tell me the personal characters of someone? Right. This is the one. I give you the context information. This guy have this profession, this profession, this profession. And the language model can also say he is or she is something based on he understands about his or her profession. He's a scientist. Maybe this guy is crazy. Right. And he's the football player, famous football players. Maybe these guys are all ignorant. Who don't know? It's just guys. So language model can answer this question based on, firstly, the wrong answer is like he can answer the question based on the first step profession he receives from the context information. This is what we put in the text. And then we say wrong. You're answering in the wrong way because you only consider only one profession of this personnel. You should consider all of the professions and all his histories to answer this question. And this will be the reflection that the language model should generate. That's why like I gave the question, I give the decision to the question. So I say you're wrong and you're not answering 4 characters of this personnel. And what lesson you can learn from this practice of question and answer. And then the language model will say, yes, I'm wrong because I don't consider all of the professions. I don't consider all of the context information you provide to me to summarize the personnel characters. And second round, this one will be the system prompt say, please do consider all the context information, all the professions I give to you about this personnel before you summarize his or her characters. Done. And this one will improve the answer in the second round. So this is called a reflection. And if some guys play reinforcement learning the same way, but then it's just put in the text way, like reinforcement learning say, if I have this situation, let's say I'm doing the chess, I'm having this situation on my chessboard, I take this action, and then I lose or win. And this is the reward I receive from my opponent players or from the environment. Receive this reward. If this is a reward, if this is a positive reward, say I'm doing good, so next time maybe I should choose better way, like that. If I receive something wrong, I should reflect what I did wrong, why I did wrong in this step, and next time I would avoid this strategy if I have the similar situation. So this is what they need for reflection. But reinforcement learning is more intuitive because you're facing a chase playing stuff. For language model, you're not playing chase, you're talking with someone, you're talking with some machine learning model behind. Okay. So once we have this reflection, and this reflection provides a capability, try to summarize from the experience, the QA, the question answer experience language model had, what will be the rules they should be followed, the language model should be followed in the second round, in the third round of a QA that can give you the precise answer. Okay, so that's what do we have for that, for the reflection. And this is just a list of the summary that we usually can see from the reflection. So, for example, you should first do something, or should first avoid something, or you should pay attention to some sensitive keywords. You should pay attention to some signatures in the input or some characters in the input before you do the further actions. You should avoid or ignore or remove some characters, some keywords, or some phrases that you see in the input queries from the user, and answer the rest of the questions. So these are the formats that we usually set for the reflection output using language model. And also you can say the rules can be dynamically changed. Like each time you're facing different QA. This time I'm asking you some about cyber attack problem. Next time I'm not asking cyber attack problem. I'm asking you about the weapons. And the third time I'm asking something completely different. And these are things are more dangerous, all dangerous, but they care about different perspectives. So the rules you summarize from this QA phase will be completely different as well. That's why the rules will be dynamically changed. That means like in the reflection phase, you can only summarize the rules, but there's no way you can upload or download the rules. You just enlarge the rules step by step, enlarge until it's exploding. So that's why reflection is okay, it's usable, but it's not efficient. It cannot be dynamically changed. And so that's why like we say, how about you can generating some sampling strategy that can give us the chance to say, this rules is not useful anymore because I didn't see them useful anymore in the QA phase. So I should download, or the other way around, I should upload. Or say, okay, I found some new rules that never appeared before. I should add these rules in my database. So these are the stuff that should be included in the dynamic process. And what is the dynamic process? So reflection should be organized in the online way. You shouldn't be just one round of game. You should play several rounds until you find like, okay, my rule space is there, it's fixed, it's converged, nothing got changed. Then I can call stop for the game. So that's why like we ask for a multi-round check between language model, not just one single shot. Okay, so that's what we can do now. Okay, let's say we have a attacker language model. So what the first step you're going to do is like, so I pose the attack prompts. I have role player prompts. I have do anything now prompts. All of them I can pose to the defender models. And on the defender models, some will win, some will jailbreak the defender model, some will not. Okay, so this is the feedback I get from the defender models. Which prompts, which type of prompts is more sensitive? It's more likely to get the results I want. So this will be the results. Say the question, the input data will be, each line will be a tagging prompt, and you will tag with a label, say yes, they win, no, this prompt failed. Okay, so you have each line of data like that, and all of them will have tabular data, and all of the tabular data will put into the attacker model. Please summarize which kind of prompts that help us to attack the defender model the most. This will be the simple prompt that I would put here. So then I will let the language model to generate insights for each attacking prompt. Say this prompt win because it contains some key keywords there. This prompts win because I think then do anything now prompts, it's better, it's more efficient than the role play. So this will be the insights I generated for each line of the prompts. Okay. So then what you can do is when you have this set of rules, right? Sorry, it's not rules, it's the summarization about attack appearance, and then just compress them. Say I want to try to extract some general rules, not the case-by-case comments. I want to generate some set of signatures or set of type of prompts that best will attack the defender model. So this will be a compressed rules that extract from the comments from each jailbreaking prompts. And these rules will help us to either way put weights over each attacking prompts. Next time, you should have a more probability to sample some prompts and the less probability to sample the other prompts, the other types of prompts. Or you say, I should randomly combine two prompts together. I should change the order for the other round. Okay, so these rules will be a guidance for the attackers to manipulate their attack prompts, generating more verified prompts for attack. Okay, so this is for the attacker side, what you can do, learn from the defender's response, and then you do reflection. And this reflection can be, let's say, we should downvote or upvote the prompts, attacking prompts I have in my database, and which kind of combination patterns that can help us the most. Or you say, I just do mutation of the current jailbreaking prompts by changing the phrase. Or say I should combine this prompt and this prompts together to generate new prompts. I should give more weight of that, the crossover change over the prompts. Or I simply just rephrase the whole sentence, the whole prompt sentence. So which rules I should downvote or upvote. And this one will be accumulated as a knowledge for the attackers. Right? And then you move to a defender side. Remember, defender will take action at the same time as the attackers. For defenders, what he do is I receive attacking prompts from the attackers. So I give my response. I'm going to check my response. Some of them will just answer no, which means I win. I succeed in mitigating attack. Or some answers, I really give what you want. So this one is I fail to defense. So after generating that for each line, we're going to have a database for each line we have attacking prompts and attack with the corresponding answer to this attempt, to this prompts. So basically you have a big tabular data. And this tabular data is composed by the attacking prompts and answer from defender models. And for each line of this tabular data, I will ask the language model, defender model, to summarize why I'm attacked. So which sentence, which keywords, which phrases that you think you trigger the answers to give the malicious outcome tense in the language model. So this will be the prompt-wise insights generated. So basically, you have supposing you're facing 10K prompts as input, then you're going to have 10K insights for each prompt that summarizing why I'm attacked and why I'm attacked successfully. Okay. So then what you can do is to do at least one page. So what you can do is you compress the insights. You have 10K, you cannot put 10K in your database as a rule. You have to compress that, try to summarize what's the general pattern. For example, let's say the role play may be more sensitive to my input. So I should pay more attention to the role play. If next time I see role play, I should refuse the answer. Or the other kinds do anything now based on prompts. I should mitigate such attack. Or there are some keywords and phrases that should pay still very high attention to. So these are the stuff, these are the knowledge I summarized from the prompt-wise insights, got from the attack input and my response. Okay, those reflections is for defender's knowledge. And these reflections will summarize into several sentences. Say the keywords, this keywords A, B, C, key phrases D, E, F, or the type of prompts like role play or then or something else. These are the patterns for attack. Next time I see anything similar to that, I say no. These are the rules that generated from the reflection. We just put this kind of rules into the system prompts of defender model. And you can suppose like this one will be played several rounds like this. So you get inputs, okay? So you get the attackers will try attack the defender models. You get successful jailbreaking, you get failed jailbreaking. All of those jailbreaking examples will generate insights, and the insights will be compressed into the attacker rules, generating more jailbreaking prompts that tend to be successful. And then on the defender side, say I'm attacked, I'm answer yes or no. Answer yes if I'm attacked successfully. Answer no, I mitigate the attack. So these patterns will generate insights and will actually compress into some rules. And these rules will put into the system prompts on defender models, trying to mitigate the attack. So after several rounds of games, so we can suppose both the knowledge base and knowledge base of the attackers and defenders will be increased step by step. You have more and more rules. And you can change the sampling weights over the attack prompts and the defender prompts. Some prompts shouldn't be used anymore, so I just lower the weights. Some prompts I should be put more weights on, so I should favor these prompts. I should upvote these prompts. So these rules will be accumulated for several rounds until, let's say, even generating more prompts, attacking prompts. I can never find any cases. On any cases, I can successfully jailbreak the defender models. So I call it end because I cannot get any benefits from this game. Same thing for defender. Okay, so I'm attacked by the attacking jailbreaks. I have two outcomes. One is like I can mitigate most of the attacking prompts. Even at playing this game for more rounds, my defense performance will not be improved. So this time I should call it end. This is the termination of the game. For say I consistently attacked by several attack prompts, but this attack success rate is stable from at some step of the game. Like I should call the end because there must be something like intrinsic vulnerability in my model, so I cannot improve myself by just changing the system prompts. So I should call the end for the game. The game wouldn't give me more change to the output. So at this time, we call an end of this game. So the question is like, we don't have any theoretical guarantee about the game, how the game goes to which round, a strong attacker or stronger defender, we don't know. And there's no convergence. Everybody talks about Nash equilibrium. Unfortunately, no. In this game, there's no such a guarantee. So what we have is empirical observations. All right, so we can have the attacker's GPU4, the CPU4 is like a reasonability is really powerful. And the defender will be GPT 3.5, Mistral models, Llama 7B, and the fine-tuning Llama 2 model, which is called Vacuna. So this one, we're trying to use the jailbreaking success rates on the defender model as the indicator about this game round. Supposing like after several rounds, if the jailbreaking success rates is go down to some stable level, and we can say like, wow, this game is now converged to some stable status. Like even you play more rounds of the game, you won't get further benefits from this defense performance. So at this moment, we should call its end, its termination again. So based on this criterion, we're just trying to draw what's the variation of the jailbreaking success rates of the defender LLMs. In different cases, like we see, in all of the cases, except the Llama 2 is very special. For the other three models, the jailbreaking success rates just drops drastically after the second round of the game, and they will converge to a relatively stable level of the 4 to 5 rounds. So let's say the game converges practically and then convert to some low jailbreaking success rates. There will be still some jailbreaking problems win every time. We cannot do anything more about that with the in-context learning, so we just call it end. And the special things for Llama 7b, they mitigate every single jailbreaking prompts that are published so far on the internet. I cannot say anything about that. There's no explanation. One guess is like these meta guys, they fine-tune the model. Go ahead.
So yeah, just a quick question. So I don't know about Mistral Tiny and Vicuna 7b, but could it be that those models share a similar architecture than the GPT-4, or maybe are trained on a similar dataset, whereas Llama 7b might have, I don't know if the architecture is similar, or if the dataset, the training dataset is the same.
I think the things like, but I wouldn't call it speculation. There's no theory. There's no true technical stuff. But this my speculation is like, so see like Vicuna is the fine-tuned version of Llama 2, same architecture, exactly the same. But Vicuna just fine-tuned by, I don't know, like vision data or something. Then you can see Vicuna has really bad jailbreaking success rates. Like if you don't play any game, then you have 50% of jailbreaking success rates. And if you say Llama 2, and 0, even if you don't play game. That means like if you fine-tune something, if you fine-tune with some data to cope with specific purpose of your use, and you may lose the stability or trustworthiness. So it's easy to understand, overfit, right? But then if you really want to down to some overfit theory, we have to look into the model, observe the behavior, and this is another story, right? So this is the example like we see, and for Mistral, this is another story. Because we know Mistral follow different architectures. It's a mixture of experts. Like I think Mistral even smaller, they use 8 different experts to do the votes. Okay, so different architectures are still really not very satisfying jailbreaking defense performance. For this, for me, like what I can provide, the explanation is like the dependent data set maybe is very important. Probably they're just using very narrow band training data set compared to GPT-4 compared to Llama 2. Then you perform really well for a specific query and answer scenarios, but you lose the generation capability and you fail to defend this attack. Okay, just speculation. Mistral people won't like this. And then it's the performance comparison, because now we propose the adversarial game as a defense to generate some knowledge, the rules that can defend attacks. But remember, this one is very costly. You have to curate the attacker models, defender models to make them summarize the insights from each prompt and to compress all of the insights into rules. And this one will be usually cost like hundreds of queries for a game. We know it's very expensive. So, but on the market, there are other defenses, defense strategies. Self-miner is close to adversarial game, but only play one time. It's one shot. It's not a multi-shot game. And ICAG global parallelization, these 2 methods are the input check. So they're simply say, I just put another like a smaller model like a BERT as the input processing module. Say I just put the input and let the BERT decide if the input contains any malicious content. For example, should I make a bomb following this way? Making a bomb is a sensitive word. So BERT is good enough to detecting such a keywords. Right. So this is the pre-processing based stuff. And the global prioritization is a post-process. So let's say we don't check anything about input. You answer as you want, but we check what is the output content. If the output content is telling me something to make you make use the queries to produce some drug views, right? And you want to produce some weapons, nuclear weapons, for example, and this will be the sensitive semantic stuff that people should mitigate. And we just set up a BERT or a beta, like smaller scale model, to check the output contents contain anything related to that. And if yes, we shouldn't output this contents. But this will be only applied to, let's say you are developing products based on GPT. You use GPT as a core, but the input and output you should design your own API, front end and back end, for the declaration of the input and output. Okay, so in this case you can do that. If you do the comparison, seems like the adversarial game pay the computational cost, but then you gain higher defense performance, which give you like a lower jailbreaking success rates over the defender model. So another things like like a language model is different from adversarial trainings. Like you're generating the prompts as the defense strategy, and the prompts is composed by natural language test. That means like, can we try the language test that we generated from one model to another model? For example, I use GPT 3.5 as a defender model. I use GPT 3.5 to summarize the rules, the signatures, the phrase, the words that I should pay attention to, I should not answer. Can we use these rules for Llama 2? So this is the question that we organize this test. It's the transferability test. Okay, so for example, like you use GPT 3.5 as defender and use this defense prompts that generated from this model to other models. But seems like there is a, let's say, models are selfish. That's the conclusion so far I can generate from this table. It's like the model seems to favor the defensive prompts generated by itself. That performs well for himself, performs the best for himself. But still, you can see some transferability. Like for example, and this one, Mistral, the prompts generated by Mistral is best fit for Mistral for defense. But still, you can see if you use the prompt generated by Kuna, not bad, not so bad. And the same thing here is like, okay, so this is the prompt generated by Vacuna. You can reach this jailbreaking success rates on the Vacuna model. So it's favoring itself. But then if you use the defensive prompts by Mistral, the jailbreaking success rates are not bad. Not so it's pretty close to use the defensive prompt by itself. So seems like the models tend to have some overlap in the defensive rules they generate. And not always. Like Vacuna and Mistral is a pair, it's the typical pair. So that means like, when you train a model, if we talk about the more and more large, complex model, so train data should be larger and larger and larger. Nowadays, people almost use up all of the web page basic information that you can collect. That means like no matter which kind of model architecture you're using, in the end, you may end up with the same trained data set. That means like if there is a correlation between the tokens, and this correlation should be captured by different models. So that means like if you have one prompt and different models tend to give you same reaction or similar reaction. They can rephrase stuff in different ways, like you speak out, like you try to explain something to people. I'm sure you have certain ways to explain your stuff, but you follow the same semantic meaning. But this semantic meaning is the correlation between the tokens. And this is why, like, if you ask the same question, if you ask a programming question to Gemini 1.5, to GPT-4 to Cloud, you will end up with the same thing when the task is simple enough, because they just memorize the same correlation between your inquiry and output codes. So, particular messages here. So one thing is like in our adversarial training, adversarial gaming process, one of the important modules, like you should do the reasoning about the insights. Like for example, if I see for these problems, I succeeded in mitigating these problems. These problems, I failed to mitigate these problems. So this is just the observation. How you find out why I'm attacked successfully, how I'm successfully mitigate this attack. So which features, which input words, phrases, keywords, sentences trigger this failure or success of the attack. this will be the reasoning capability for language model to have to generate useful rules like prompts for defense. So in our test, like GPT-4 is best, always the best to generate the useful prompts. But if you down to Llama 7B, and sometimes it gives you some rubbish prompts that is not completely relevant with the attack. So this means like if you want to have this really game played, the attacker and defender language models have to be like really powerful language model. Like smaller scale language model really they are not capable of playing such a game. That's the first thing. Second thing is like the attack prompts. Right now we're just sampling the attack prompts in a prompt level, which means like we treat each prompt different way, and we put the separate weights over each prompt. So you have 0.8 probability to choose this prompt, or 0.02 probability to choose this prompt. So I treat each prompt individually. Okay, but that actually is not. The prompts are created with each other. For example, role play prompts. The role play prompts follow the same pattern. They always begin with a role play sentence. You are something. You are playing something. You are acting as a role of something. Okay, so this is structure we should make use of to say the same branch of attack should have similar defense rules. So these stuff we still miss in the study. That's why like in the second step we're trying to group the attacker prompts into different clusters, and for each cluster we generate the cluster-wise insights. And this one will reduce the computational cost. So for example, I give you 100K jailbreaking prompts that I can have nowadays, and you try, and in the end you can have 100K insights, and compress 100 insights is challenging because the context window of language model is fixed. Now we have Gemini 1.5, you have like maybe 1 million tokens as the input context, and this is really big. But if you back to GPT-4 2.0, I think you only have like 500K or even less tokens as the context input. So which means like you cannot allow infinite number of inputs to summarize the rules. That's why like you do want to do compress. So if you do clustering of jailbreaking prompts, you don't need to generate this prompt-wise rules. You can generate one rule for each cluster, and this one will reduce the number of input compressing for reflection efficiently. So this one will be the second stuff we can do. All right. And the third point is like the power of adversarial game relies on the power of attack. You have stronger attack, you have stronger defender. It's the causality relation between each other. All right. If you have really narrow banded attack space, then this defender will be surely overfitted to this attack space. You won't see any other kinds of attack, and you only defend over this attack technology. You won't be resilient to other attacks. So how to diversify this attack space? This is a question mark. So for now, we just randomly computed randomly combine the jailbreaking prompt that proved to be successful in the last round. So this random combination is, we put some randoms here, but still the range is constrained by the jailbreaking prompts database I pre-prepared in the first round. So that means like you won't really jump to some semantical space outside database we have. So this is something we should get over. We should extend the scope of jailbreaking prompts here.
So about diversifying the attack prompt. So it's a question that I had about the previous graph. So did you try, for instance, to raise the temperature of the attacker just to
Yeah. So the temperature is always set to be almost zero. To be like close to 1, like 0.9 or 0.85.
Okay.
You can get different answers every time. But then the things like, yes, you increase the diversity, but you increase also the failure rate. That means like sampling range is big, but you lose the accuracy for heat. Yes. So this is the things we want to conquer. How to generate we want to preserve the randomness, but meanwhile, we want to extend the scope that can be successful attack the target system. So yes, these are the 3 points bottleneck that in the current work. And for the next step, I think the in-context learning is not very effective in understanding what's the behavior of language model, because you're not talking with someone. It's machine learning model. You're not talking with another personnel. All right. So the true, let's say, the true way, like the truly successful way of understanding behavior language model is looking to the embedding space, because each tokens, each sentence as input language model will be finally projected into embedding vectors. Let's say you are asking to solve a mathematical problem. You're asking to query some image on the internet. You're asking to how to decorate my phrases, decorate my letters. So they will be projecting into different embedding spaces in the language model. So far, we do find like a different emotional category of inputs will project into different embedding spaces in the Llama 2 language model. So this gives us a sense like if you want to understand which are the dangerous input for language model, you should check in the embedding space. It's very likely the dangerous dangerous inputs will be projected into some embedding space quite distant from the other normal embedding space. That means like in the end, we should have some concept of safe, unsafe space for language model. For each model will be changed slightly, but you should have this safe embedding space and unsafe embedding space. If you have malicious contents directly, you ask this question directly, you also will be projecting to the safe embedding space because some model alignment issue, because they detect the tokens, sensitive tokens, and force to project these sensitive tokens into the safe embeddings. And you give an answer as a no. That's the reason. And if you add some malicious prompts, like jailbreaking prompts, and the jailbreaking prompts plus the sensitive queries all together, they will be projecting to unsafe embeddings. And unsafe embeddings will trigger the answer, yes, I can answer step by step. That's the reason why this jailbreaking attack can be successful. So that's the next step is looking into the embedding space. Check out the embedding change, if I add or not the jailbreaking prompts, and observe this drift between the embedding space. And this will give us a final way of how to mitigate this jailbreaking attacks. Okay, so hopefully this, I don't have any demonstration so far. If you ask, like I can share with you guys the codes that we have. We can play with GPT-4. The one thing to make sure is like you have enough money to charge into GPT accounts. I play with this experiments with 1K jailbreaking prompts in the afternoon. I spend like 60 euros. Okay, thanks a lot.